Hi everyone, welcome to the Azure.NET user group right before the Christmas. I'm going to present you real-time face recognition with Microsoft Cognitive Services. So I am JK, or pronounced Jernej Kavka, software architect from SSW, and you can follow me on Twitter, GitHub, or blog, and I promise that next year there'll be plenty of posts. Right now it's just one. And today I'm going to present you something different. I won't be focusing as much as using the APIs rather than how to use them in real life. In this scenario, in real-time recognition. And I'm going to start off by introducing SSW Sophie, which is a solution we use to recognize people and show them some content. Then I'll show you the challenges we had developing that product and how you can improve the face recognition even further with specialized cameras. So to start off, first some definitions. Face detection or face tracking is usually meant when you try to detect a face. You roughly know its shape, you may know its gender, its age, but you don't know its identity. So that's very important to know, because the next one is face recognition or identification, which actually identifies the detected face. It's very important when you deal with that because you have separate algorithms for detection and separate for recognition. So let me quickly introduce SSW Sophie, like real quickly. This is our solution for the smart office, and at the moment it's in the reception area. And when a user comes in, it detects that user and it shows a relevant information for that user. So we show things like Power BI and their appointments and things like that. But to keep long story short, I'll just show you a quick demo. So this is the application, but the best way to see it in action is through a video we have prepared. And if anyone is interested, I can show them behind the scenes of how we set up the hardware in our Sydney office. But in interest of time, I'll just give you a high-level software overview of Sophie so we can then go to the challenges. So for a user to be identified, we first have built a camera server which only captures the images, and that images are then sent to Microsoft Cognitive Services. That image is recognized, and we display some relevant content to that TV. Now, it sounds easy, and in matter of fact, it is. And I'll get back to that real quickly. But first, I want to touch why we chosen cognitive services against, for instance, offline tracking or other solutions. So one of the main reasons is easy implementation. As you've seen previous slide, we have a really simple workflow, and I'll show you that in code, it's actually really almost that simple. Then you have easy to scale. So because it's on the cloud, you essentially can scale it as much as you want. You have almost infinite power, theoretically. You have one unified database. This is very important if you have multiple offices over the cities or even countries, and you really don't want to share a couple of gigabytes of training data across different servers. This is one problem of the offline face recognition algorithms, where basically you have to transfer a lot of data, and they're not easy to implement either. We thought we're going to have problems with the speed of face recognition, but we're aiming for less than 2 seconds for each individual, and we are currently getting 500 or less milliseconds, which for our case is more than enough. And it's available everywhere. Where's the internet? So you can call it from Android, you can call it from iOS or desktop. It doesn't really matter, as long as it can capture an image and send it to the internet. They can call the cognitive services, and they can get identity back. And here's a really quick run through how to use face APIs. You usually get this in 30 minutes, but it's super simple. So the easiest way is to use C# and that NuGet package. How many of you are using C#? So roughly half of the room. Don't worry about it. The commands here almost roughly goes one-to-one to the post APIs, and if you are interested in, I can show you the website, the Microsoft Cognitive Services website, and they really show you nicely how easy it is to call. It's essentially a REST API. And first we start off to initialize a face service. We put in a subscription key. Then we put an image into a stream. So we either capture it from a camera or from a file system. And this is one part of the magic. We call detect, and we get all the faces that were detected on the image. We send those faces, the list of those faces, to identify method, which basically does just a web call to identify all the faces and returns back the potential users. And all we are left to do is go through the candidates for each potential user and say, yeah, I'll take this user because it has high probability. And most of the cases, the users that are in the list, the first user is really close to what you want. And that's all about it from the code perspective, and that's the only time you'll see this some code in this presentation, because the big challenge isn't the Microsoft Cognitive Services. It's just a tool to achieve something better. So let's go to the challenges. So first challenge, and one of the surprising challenges we had, is it can cost a lot. And I'll come back to that, but we were a bit surprised. You'll see a lot of demos where they push a button, they get an image, everything works well, and they can run it on free tier. They even have it deployed on doors. They ring the bell, they snap a picture of them, and they can use it for free. But we're talking about here real time, so that changes a lot. We are doing a lot of API calls. You have noticed we're doing free API calls back then. And we're also having issues with blurred images, and most of them happen to low light conditions or because people are moving pretty fast. And we want to also know whether the people are in front of the devices or when they left. So we kind of need to track them. And the quality of cameras really impacts on how you're going to do the recognition and the quality of recognition, how many times you're going to miss a person simply because it was blurry or it wasn't light enough. So let's first check the cost of the Face API. The free tier seems to be nice. You have 20 transactions per minute and maximum 30,000 transactions per minute. In most of the cases, if you don't do real time, this should be pretty good. And the standard sounds amazing. You have 20 transactions per second, and for each 1,000 transaction, it costs you $1.80 US dollars. But what happens if you do a naive implementation? It can bump the cost up to $100 per day. And that's US dollars, not Australian. So why does it cost so much? You might have seen a little glimpse of it in the code sample. For one API, for one detection of one person, you have to detect the face, you have to recognize that face, and if you didn't cache, you have to get the user data. These are 3 API calls you have to do. So in 1 minute, you have only a certain amount of available calls you can do to recognize people, and you cannot do real time. And it gets worse for 3 people or more. The face detection and face recognition has the same amount of calls. But if you don't do the right thing, when you try to get data from all of the users, you need to call one API for each user. So you have 3 API calls for 3 people, totaling 5 transactions. And then that scales linearly. And we'll see what's the naive implementation. Just to give you a bit of scale, how quickly you can get to a high cost. So I've taken a case we actually had in our company. We took one picture every 5 seconds for 24 hours. We assumed that we'll roughly detect one face for, in average, the entire day. So we might not detect the faces all the time, but we average it into one face over the entire day. And that comes to 36 transactions per minute. So we are way over the the limit of the free tier. And that's about 52,000 transactions per day. Now, those 1,000 transactions doesn't sound that a lot anymore. And recognizing one every 5 seconds isn't that quick either. When you miss that window, for instance, if one person comes in and another person comes in a little bit, just a fraction of time too late, they have to wait 5 seconds, and it can be painful. And if the face recognition didn't work properly, they have to wait another 5 seconds. So this is pretty horrible and expensive. So how can we fix that? And it's really not that hard. So you can cut the cost by at least by 1/3, just by caching users and groups. But that's easy. If you look at the code, that almost was obvious. Unfortunately, you cannot cache face IDs because each time when you send a request, you get a different face ID, even if that face was similar to the previous one. But here we come to where you use offline algorithms like face detection that detects only a face. doesn't know the identity of the person, to save the bill. And what we do is simple. We run the algorithm over the image, say, there's a face, we send it to cognitive services. If there's no face, we don't send it. So on the weekend, we have zero cost. And you might find that those algorithms are pretty easy to implement. In fact, in C# UWP, the Universal Windows Platform, you have a very simple SDK sample where you can implement that super easily. Works on most of the cameras you can plug into Windows. You have quite a few libraries on JavaScript, and Android and iOS has pretty much built-in functionality of that. So it's really not that hard to implement that, and that saves you a lot of money. And face recognition is still done on cognitive services. So you still keep that simplicity of recognizing people, because that's actually the hardest part. That's where you have database of gigabytes of faces, and where you have algorithms that bumps your CPU to 100% every time you try to recognize a person. And this is a simple example of a built-in application in Windows, Windows camera app that has built-in face tracking. And exactly the same APIs that the Windows camera is using, you are using in your applications. So just to quickly show you, I have here a Kinect camera. Sorry about that, I need to close the previous one. Actually, I can just show you the camera we're using here. Sorry about that technical issue. One weakness of UWP application is if you minimize them and restore them, and using Kinect, they might freeze. So don't minimize them. So as you can see, there are a couple of faces here recognized. And this is something that you can implement really quickly, just in an hour or two into your application.
Is there a difference between blue and white?
I think it's just different people. I'm actually not sure. Yeah, it basically, one time I was white and the other one, this gentleman was white. So yeah, that's the simple part. Now, we kind of touched on tracking users, why we would do that. One reason is, to know when. Sorry about that. Oh, okay, found new functionality in there. So, one reason is to figure out whether the user actually is looking at the screen. So we can decide whether to still show the content or not. But the other one is far more bizarre. Did you notice how many faces there can be in one place, or how the number of faces can change when you don't expect? Let me show you a real-world scenario that actually happened in SSW Sydney. To better understand, we made the setup of SSW Sophie with all the camera, hardware and everything before the office was fully furnished. And what happened one day is this. Like you can see here, we had like nice expenditure. We didn't really went and over $5 any day. And here you can see we have the weekend. And what happened here? So how many would like to guess what happened on this day? Yeah?
I reckon if you're doing a fit out, all your workmen came in and out, fitting out.
Nope. Anyone else wants to try?
Someone bring a photo of a person?
Close.
Close. Oh.
We added our SSW ads. And this guy cost us this much. But you know what? He was worth it. Yes. But it was a good lesson that faces can pop out of nowhere, and they can stay in one place without you knowing. And that has real effect on the bill of your application. So keep that in mind. And this is usually a problem with real-time tracking. When you press a button, make a picture, you usually don't have that problem because you control how many times that happens. So the solution for that is when you have a face, you can, with the offline detection algorithms, you usually get a rectangle like this. So you have the data of how big the face is, and then you can calculate its center and its relative size. And then you can just use simple algorithms to send the image only when the face have moved for a certain amount. So for instance, if that face moved from here to here, so if I move like this, maybe that's a good time to make a new image because the face moved rapidly. Because this is a simple solution, we don't really know if somebody else come into the view and we lost that face because of the blur or because there are various things that happened with offline face detection algorithms simply because we don't have a full picture of what's going on. So it's the simplest way to solve this problem is just have simple math, calculate the centers, and calculate the deltas between the movement of the faces. And allow to have a couple of frames being dropped. So if the face suddenly disappears, wait a frame or two to get back the face. You usually find that on 60 frames, there are like 2 frames dropped on a good camera. And the other thing is, it all sounds quite logical, but if you get suddenly 3 faces, out of you had 1 face and now you have 3 faces, you'll do another recognition. But these are the simple logics that saves you more than 95% of the money. They save you from that huge spike when somebody put that ad on the wall, simply because that face doesn't move. And the last part I want to touch on is the quality of cameras. There's a reason why I have here Kinect, and currently it doesn't use infrared and depth sensing streams, but I'm still using Kinect over webcam, is the quality. So the reason, so basically why you want to have a quality camera is if you don't have enough pixels, imagine you have to cut out the faces out of the image and then send it to the cognitive services. And from that image, the algorithms have to figure out, okay, this is this face. And if you don't have enough pixel density, if a face is slightly too far away, nothing will be recognized. And the other thing is, especially in situations like this where you have only artificial light, a lot of webcams and poor quality cameras don't work with artificial light. They're terrible. And there is also one important thing. Some quality cameras blurs individual frames to make the image appear more lively. Like certain TV sets, they basically smooth out the frames. This is very bad for cognitive services and in face detection and recognition in general. So avoid those cameras. And you have to have a camera that can auto-correct the colors and basically try to do the hard work of figuring out what's the best picture. And that's why Kinect is also really good. Oh, and you want to aim 30 to 60 frames per second, and not just for gaming. So just to recap, the bad stuff: don't take 480p webcams. Bad images will be always a bad resulting cognitive recognition. And the biggest issue is actually unstable frame rates. Because a lot of face detection algorithms, I found they work really poorly when the frame rates are down. Even though the quality of the image didn't degrade that much, for some reason, the number of times the face is recognized have decreased significantly. So one example of artificial light is here you have the Kinect Vision 2, and here you have a laptop webcam. And here you can see the image is much brighter, and you kind of see more pixel density, even though the image isn't really good. But remember, this is under artificial light. This isn't a really brightly lit up room. It's less lit up room than here. And to just show you a close-up, here you can see my eyes and my glasses just normally. And here, the frame of my, my glasses almost blend into the eyes. And that's a problem for face detection and face recognition algorithms. And you don't want that in your cameras. So now I kind of showed you what we had challenges with Sophie and the solutions we had. The simple solution is just to use a quality camera. But when we got a Kinect camera, we said, can we do something more? Can we not just do a good facial recognition? Can we get something better than that? And we had, with infrared cameras, what you can do is see at night. So you can turn off all the lights and you can still see. Why is that important? The first person in the morning is the one that will be in slightly darker shade, and the last person going will probably be in a bit darker environment. And even at 5 p.m. on winter time, especially in Europe, it's so dark and the artificial light doesn't give you enough light to see. So I'll give you a challenge. Can somebody tell me which of those two pictures was taken on low light condition? Is it the right one? Anyone to have a guess? Which one is for the right one? Which one is for the left one? Ah, you're good. Yeah, the left one was done in low light conditions, and as you can see, you can only see my TV outside behind me. You can recognize nothing in that picture. And here you have in quite well lit room, but from infrared perspective, it's the same. Now, you won't get the same experience on all infrared cameras, but the Kinect camera has really, really good infrared sensors. And what it also cannot see, which is a feature, is basically any projection or screens. So if you look at here I have iPad, but when you look at the iPad on infrared, it doesn't see anything. And I actually use that knowledge in a project in the past where we had projections and we had to do mixed reality. And we used infrared in order to track users, because we completely ignored what's projected. We just saw the stuff that there is. They could put their phone and we wouldn't be distracted by the light. But unfortunately, it can see paper. So if somebody prints out your face and put it in front of your infrared camera, it will recognize it. So you can't really use it completely for security infrared, but it's pretty close. Most of the people would try to fake it with iPad. And the next one is the depth camera. So the depth camera has a little bit interesting view on the world. It basically sees each pixel in millimeters. So here you have my room. You can see a sofa here, and this is a corridor. So the first time you look into it, it might look a little bit weird, but when you see this as a corridor, you start to get a feel of how the image is represented. And the other thing that depth cameras can give you is skeleton tracking, which is much more stable than face tracking. And we'll go back to this one a little bit later. And one interesting security thing is it cannot see any content on 2D media, on any 2D surface, with a little bit caveats, which I'll show you here. So here you can see my TV and iPad. You can't see anything. But here you can see I have a thank you card, and you sort of see something in the middle. So while this might seem a problem for some, this is just a infrared absorbent material, and that's why Kinect sees a bump in it. But in fact, if you try to do this, if you wanted printed out a face that depth camera could recognize, you'll have a lot of hard time. It's easy just to make a 3D printer, have a person in front of you and scan their face. But they have to know about it, and they have to stand and have high resolution 3D scans, which isn't exactly easy if you want to get their face without their knowledge.
Unless they're asleep.
Yeah, but our focus wasn't too much on security. It was more about potential of the security. So we know if we use Kinect or a Kinect-like device, we can actually implement something like that. We're more interested into skeletons, because face tracking, you can easily lose a face. So if I stand in front of a camera and I have a person next to me and I want to say something to that person, I turn my face away. And that moment I lost contact with camera, and camera doesn't know I'm there. And the other problem is the images are blurred. The face turned away. And if you have big sunnies, you might actually not be recognized simply because it covers too much of your face. Or if you have a hand that covers it too much, it won't detect you. Now, the problem is that face recognition might also not recognize as well, but Microsoft is working pretty hard to combat that as well. But there's a limit how much you can do. You can just see the problems with Face ID on iPhone X. You still need to put your glasses down. And another problem is it heavily relies on the image quality, which we saw that it can be pretty bad at times. So skeleton tracking is very stable. I'll show you that in a moment. And what I mean by that is, if here I have the Kinect camera, and if I turn around like this, it will still track me as the same person. If I turn around, it didn't lose me. It just knows that I have made one rotation. And that's amazing. And you can have big sunnies, you can have a hat. Still, It will keep track of you. And it can work in less than idle images, simply because the original images are really bad. And they have really good algorithms to combat that. And their algorithms are super sophisticated and stable. And what you can do is, once you have a skeleton, you can just detect their face, recognize that face, and then pin that identity to that skeleton. So the next time you try to say, hey, what people I have on the frame, you can just check your skeletons and see if they have identities pinned to them. If they don't, you try to re-recognize them. If they have, your job is already done. And you know the position of the head in real time. So what it knows is not just, here's the head. They know, it's looking right, it's looking left, it's looking down, or it's looking completely different direction. So what you can do is say, hey, if the user isn't engaged with the screen for more than 5 seconds, we just regard it as the person isn't interested in the content, and we can switch to another user. And I'll quickly show you, actually, if you're interested, I can show you the demos at the end, because we already got the pizzas. And I'll quickly go through the demos. Just quickly one demo with the skeletons. Wanted to show you the colors and the infrared real-time streams. So here you can already see we have a couple of skeletons already being tracked. And you can, for instance, look a different way. And it will still track you. It won't be able to track... It won't be able to track all of your joints, but it will be able to track you good enough. So if I just hijack a little bit, so what I can do is turn around, and it will still track me, no problems. So this is the quick demo. So one last part, and I'll get you to the pizzas. How do you connect that to Microsoft Cognitive Services? You'll notice if you work with infrared and depth images, they're 16-bit in size, but the Cognitive Services only works with 8-bit. So you have to convert them to a lower resolution for each pixel. And that means you may need to do some pre-processing, because if you just reduce the number of colors per pixel, you might get something like this. So see how everything is cut off, or see how it kind of lost the contrast. You just have to slice the image, the range of colors that you're interested in, and then convert that with as little loss as possible. We could do an entire talk just about things like that. And what you need to do is retrain Cognitive Services with those infrared and depth images. You can have multiple streams of images for each person side by side, but you need to do them with those cameras. You cannot just do the grayscale filter. I tried it, didn't work. And the other thing is, if you want to use Intel RealSense in Kinect sensors, be prepared to implement 2 different APIs. Unfortunately, there's no unified camera APIs to access the infrared and depth streams. So now, I'll just go through this. We know it's easy to use, but it has some challenges. You need to be aware of the costs, you need to be aware of the camera, and you need to be aware of the environment. Once you're mindful of all those, the cognitive services is really good. And despite those struggles, we're still sticking with cognitive services. But in some cases, if you don't have internet, if you don't, if the environment is such that you need to react immediately, you may want to implement offline face recognition. But in most of the cases, cognitive services is really great. So thank you for watching, and the pizzas are ready.